All right. I'm going to walk through this example problem on using the rate determining step method to develop a rate law for a reaction. So this is example problem 5.9 from the Rawlings and Eckert textbook. So what it says, the synthesis of methane is carried out over a ruthenium catalyst, and we're given the reaction. One possible reaction mechanism is, and it gives us a mechanism, says step 8 is the rate determining step, right? The rate law for this reaction in terms of only reactant and product species, that is, do not include any surface concentrations of intermediate species. Okay, so we're gonna write this we're gonna basically come up with a rate law here using the rate determining step method. And the reason that we might use the rate determining step method in this example, this is a catalytic reaction. Because it's a catalytic reaction, likely what is happening is that a lot of the steps on the catalyst surface are relatively fast because the catalyst is promoting those. And so only one or two is going to be slow. And in fact, we know that step 8 is going to be the rate determining step. However, we know because of the problem statement, maybe not explicitly written here, but I know because I got this from a textbook, that reaction 3 is also it's at least not reversible. So there's 2 steps that maybe go into our slow step bin, and then there's the rest of the steps, 6 steps that go into our fast step bin. All right, so to start this, let's make some assumptions. So I'm going to make assumptions about fast and slow reactions. Since this is the rate determining step method, when I say a reaction's fast, I say that the reaction is going to be quasi-equilibrated. So that's different than in the pseudo-steady state hypothesis method. In the pseudo-steady state hypothesis method, I say the net rate of generation of some species is equal to 0. In the rate determining step method, I say these are all my fast reactions, and the net rates of those reactions is equal to 0. So it's 2 separate methods. Typically, the rate determining step method is used quite a bit in catalysis. However, I hope to show you later in the semester, if we have time, that in reality, both methods are used. But today we're going to look at RDS. Okay, so first step, I'm going to make assumptions about these different steps. I'm going to say that step 1 is quasi-equilibrated. I'm going to denote that as QE. Step 2 is quasi-equilibrated. I'm going to say that step 3 is irreversible. Step 4, quasi-equilibrated. 5, quasi-equilibrated. 6, quasi-equilibrated. 7, quasi-equilibrated. And I'm going to say that 8 is not only irreversible, but also it's the rate determining step. Okay, so if step 8 is the rate determining step, that means that the rate law for this reaction, let's say RCH4, so the rate of formation of methane, and if we want to be clear, that's going to be methane gas, although I guess I don't need that because there's not absorbed methane, so that's going to be equal to the forward rate of step 8. That's going to be K8F theta CH3 theta H. And so recall here that the thetas indicate surface concentrations. What those variables are denoting are the number of adsorbed species either per metal site on the catalyst, or catalytic site, or per surface area. So it's either a amount per surface area or it's amount per catalyst site. Usually the number of catalyst sites per area is known, so really those 2 quantities are identical, or at least they are relatable by a constant. But you can think about the thetas as being surface concentrations. Okay, so if I want to solve this rate, what I need to do is I need to get rid of the surface concentrations of intermediate species. And the reason that I want to do that is because those are hard to measure. So I want to be able to write those in terms of gas phase concentrations. So I'm going to need, at the very least, I'm going to need to solve for the concentrations of CH3 and also of H. Okay, so let's see here. For CH3, I'm going to use reaction 7. So we'll say theta CH3. I'm going to say use reaction 7. Okay, so reaction 7 is a quasi-equilibrated step. That means its net rate is equal to 0. And I can write out the rate law for this reaction when I have any sort of mechanism. Actually, if I am writing a mechanism, then usually all of the steps are elementary steps. So I can, very easily write out the reaction mechanism, the rate law for those reactions as elementary reactions. These are all quasi-equilibrated. That means that they have forward and reverse contributions, and because they're quasi-equilibrated, the net rate is equal to 0. Okay, because that net rate is equal to 0, that allows me to turn this rate into an equilibrium statement. So I could take the equilibrium constant is going to be equal to the reactants over the products. I can get that just as well by solving for the coverage variable I want here. So I'm going to say theta CH3 is going to be equal to KC7. So KC7 is my equilibrium constant times theta CH2, theta H, and then divided by theta star. Theta star is the fraction of free sites, or the number of free sites on the surface. So depending on if you're normalizing by number of sites or surface area. Okay, so that gives us an expression for theta CH3, but unfortunately this brings in two new variables, theta CH2 and theta star. Let's solve for those. Okay, so let's get theta CH2 first. So we'll say theta CH2, and we'll say use reaction 6. Yes. So reaction 6, I'm going to say 0 is equal to K6F theta CH. And again, I'm writing down an elementary step for this reaction, assuming it's reversible, and that the net rate of this reaction is equal to 0. And in doing that, I can solve for this coverage. In doing this, we notice that I introduced another coverage term, so now I need to go back and get that. So I'll say theta CH. I'm going to say use reaction, I'm assuming 5, yes. So I can write down the rate of that reaction. It's also quasi-equilibrated, so the net rate is equal to 0. That allows me to solve for theta CH. Okay, now I need the coverage of carbon. See, what I'm doing here is I basically want to eliminate all my coverage variables. So every time I get a new one, I have to go back and solve for it. So carbon, that's going to come from reaction 2. So 0. Okay, so now I need theta CO and theta O. I'm going to try for theta CO first because that one is relatively easier. I'm going to use reaction 1. So we'll say 0, K1F, CCO. Okay, so now we're getting somewhere. So we're getting a gas phase concentration finally, instead of a coverage variable. This allows me to solve for my coverage variable. That's going to be K1C, or I guess I should maintain the same notation. So C1, again, that K, uppercase KC is an equilibrium constant. C, CO, and then theta star. All right, so now I need theta O. And I don't have a great way to get that. I've already utilized all of my equilibrated reactions. So all of the quasi-equilibrated reactions, I think I just exhausted all of those. So I can't use any more of them. I can't use any more of them to get this oxygen coverage. Because if I do that, I wouldn't have a set of independent equations, and I'd get myself into a circular loop. So what I'm going to do is I'm going to use this reaction 3. Maybe not the best option, but it's what I've got, right? So this is a model. When we do mechanisms, a lot of time we're constructing a model, and we're going to compare with experiment and hope it works. So let's try something. Okay, so we said that reactions 3 and 8 are irreversible. Let's assume that R3 is equal to R8. And we're going to assume this because reaction 3 produces water and reaction 8 produces methane, and those in the overall reaction are produced in stoichiometric amounts. So it is not unreasonable to say that they would be produced at the same rate. So we'll say which is reasonable since H2O and CH4 are produced in stoichiometric amounts. Okay, so if we do that, then what we're saying is that K3F theta O CH2 is equal to K8F theta CH3 theta H. Here, this is the gas phase concentration of molecular hydrogen, so that is useful because that's not an intermediate species, that's a measurable amount. If we then use this expression and solve for theta O, that gives us this expression. Okay, now we should have expressions for all of our coverages, so we can start making substitutions. Let's go back and write our original rate law. I've even forgotten what that is. Let me go back and grab that here. Okay, so we'll say restate rate law, just because my solution has gotten pretty large at this point, and I just need to remember it. I realize that I haven't gotten theta H yet. I'll get that later. Since it shows up so many times, I'm just going to wait and get it later. It's also a relatively easy one to get because like CO2, like CO, it's just going to be an absorption reaction. So I'll go grab that in just a second. Okay, so first, let's start substituting in. I eventually want to be able to have an expression for theta CH3, and I do have that. What I'm going to do now is I'm going to substitute all of these CHX terms into this expression. So I know that theta CH3 is going to be equal to KC7 theta CH2 theta H over theta star. So I'm going to now sub in, I guess I should say here, as I'm trying to make my solution organized, I should say, here, let's do this. Restate rate law. We'll say, oops, that's not very well written. So I'm going to develop an expression for theta CH3. Okay, so that's the expression, but of course I have these other terms in here, so I'm going to go and sub in my expression for theta CH2. That's going to give me theta CH3 equals KC7, KC6, theta CH, theta H squared. You see why I'm going to kind of wait on my free site coverage, or my concentration of free sites and my concentration of hydrogen, because I'm going to accumulate a lot of those. And so I don't really want to sub them in quite yet. I'm going to wait and do that at the end. That's just a personal preference, by the way. Next, I'm going to sub in theta CH. So we'll say that their theta CH3 is equal to KC7, KC6, KC5, theta C. All right. Next, I'm going to sub in for theta C. All right, KC7, KC6, KC5, KC2, theta CO, theta H. Oops, that should be cubed. Theta O, theta star squared. Okay, so now we're gonna sub in theta O. Where am I here? Theta CH3. Say K3F over K8F CH2 theta CO. I'm running out of room. Okay, so now we're getting somewhere. Next thing I'm going to do, I see I have two instances of theta CH. I'm going to combine, or I'm sorry, theta CH3. I'm going to combine those. So we'll say rearrange. And I get theta CH3 squared equals the rest of this stuff. Okay. Now, let's sub in theta CO. And I guess we can also sub in, at this point, let's sub in, let's sub in both of these. Theta H, I would need to go and get that. Let me do that. Let's say theta H. And we'll get that from, hold on, reaction 4. So we'll say K4F CH2 theta star squared minus K4R theta H squared. That gives me theta H is equal to theta star times square root KC4, CH2. So then, going back, we're going to keep working on this expression. There's a joke about I-94 in Michigan. It says, be like I-94 and keep working on yourself, no matter how inconvenient it is for everyone else. Maybe that's the way we feel here about theta CH3. So we're going to sub these in I'm going to run out of room again. Okay. This will be squared. All right, I think I got all that. Let's start combining. So we have a lot of constants here, a lot of equilibrium constants, a lot of rate constants. Really, we're not going to be able to measure all of those individually. What we're going to get is kind of a lumped rate constant. So let's save ourselves some algebra and lump them, right? So experimentally, we would only get one lumped rate constant. So there's no reason to carry all of this information through, at least not right now. So let's combine. So we'll say, let's just call this K prime, and that's going to be equal to we'll say to the 1/2. Okay, so now we can simplify. And we'll say theta CH3, K prime, CH2, CCO to the 1/2, theta star to the 1/2. Okay, so now we can put this back into our rate law, finally. So you can say RCH4 is equal to K8F times theta CH3 times theta H, and we now know that this is going to then be equal to K8F K prime CH2 theta H CCO to the 1/2, and then theta star to the 1/2. Now we got to get rid of this instance of theta H. So we'll say sub in theta H. And where am I? That's going to be RCH4. All right, so let's combine some constants again. So combine. And again, whenever we have multiple constants multiplied together, or even constants like added together, we are allowed to group those. So let's say that K, this is a rate constant, K double prime is going to be equal to 8F K prime KC 4 to the 1/2. Then RCH4 is going to be K double prime CH2 3/2 C CO to the 1/2 theta star to the 3/2. Okay, so now the only intermediate term I have is this theta star, which is my vacant site concentration. So I get this from the site balance, and in fact, let me say theta star. I will say, get from site balance. Note that I am writing this in blue, whereas every other time I wrote a reaction that we're going to get something from, I wrote it in red. So what I'm doing here is I'm writing my assumptions in red. So when I'm getting my other coverages, I'm making an assumption that I can get those coverages from that reaction. In a lot of cases, it's the only choice, but in some cases, I could get multiples. I could pick a reaction. I could get multiple species from one reaction, so I have to make a choice. So that's kind of what I'm doing. And I may be right and I may be wrong. I mean, this is kind of the issue with mechanisms, is you just kind of got to work through the algebra and see what happens on the end. And if it doesn't work, you just gotta do it again. So I don't always know the right way to work through it. So I'm making those assumptions. When I go to theta star, I'm always going to get that from the site balance. So the site balance, what that says is that the total number of free sites, or the total fraction of free sites, if I'm talking about total number, it's going to be theta total. If I'm talking about total fraction, it's going to be equal to 1. That's going to be equal to the sum of everything that could potentially be on the surface, including the free sites. So that's all my different species. Now what I'm going to do, the problem statement, and I guess I don't know if I typed this in here, but one of the things that's given in the original problem statement is that the surface is dominated by CO. This means that that most stuff has low coverages, not zero, but lowish. Coverages maybe on the order of 10 to the minus 4, 10 to the minus 5, maybe lower than that. So when I do my site balance, I can make assumptions that those are equal to 0. So that's basically saying that I want to be able to quantify my free site coverage, and I'm not going to worry about things with very small surface concentrations. Now I can't do that when I'm going through and writing out my rate law, because then my rate law dependence is gonna, it's not gonna have dependence on various things which might matter. But if I'm trying to quantify the number of free sites on my surface and some of the different coverages don't contribute much to that, I can certainly estimate them as equal to 0 in this circumstance. So I'm gonna say that everything except for CO is approximately equal to 0. That gives me just the total number of free sites, the coverage of CO, and the total number of sites. So then I can use that to solve. So I'd say then theta tot is equal to theta star plus KC1 PCO theta star. So then I can say theta star is equal to theta tot divided by 1 plus KC1 CCO. So the theta tot, again, is either the total fraction of free sites, which if you're doing a fraction, then total fraction is 1 or 100%. If you're doing total number of free sites, that value is usually known. So it's okay to have that quantity in our equation. Okay, so we could kind of take this as is. We could just take this expression. But another thing we can do is if we say, we're going to say that, we'll say that the free site, the coverage of CO is much larger than the coverage of free sites. If that's true, then what we're essentially saying is that KC1, and that's pressures, I should be using concentrations, is much greater than 1. So then I can simplify my free site coverage even further. If you're using a computer to solve, you don't probably need to do this because you've already got something that's pretty simple. But if you're solving by hand or trying to understand reaction orders and you want to simplify out your expression, you can certainly make this assumption, as long as it's valid. In this case, it is. And we know it's valid because we were told in the problem statement that we can make that assumption, even though I forgot to type it into this particular problem statement. Trust me, it's there. So then we can substitute say R so then that's going to equal and then if we again combine constants, let's call this K triple prime. In fact, let's just call it KF. It's really a combination of a bunch of constants. Did I skip something? No, I'm good. Okay, so then that would be my final rate law. And we see that it is it's 3/2 order in H2 and it is -1 order in CO.